Okay, so today I'm happy to present Grisha Konovalov, who will tell us about the cotangent complex, its properties and applications. Please, Grisha, take it away.
Hi everyone, thanks for having me, and thanks for coming. Today I will talk about cotangent complex. I will define it, and then I'll try to tell you what it's good for in terms of the deformation theory. But first, let me start with a recollection from classical commutative algebra and classical algebraic geometry. There people defined Kahler differentials, which plays a similar role as the cotangent complex does. So let me recall what that is. So let A be, and let me also mention that I will throughout the whole talk I will work over a field K. Let me fix a base field K, and I will assume that it has characteristic 0. It's possible to do all the stuff I'm going to talk about today in a characteristic independent way, but I chose not to do that for the sake of simplicity. So let A be a commutative K algebra, a discrete commutative K algebra. There is a model of Kahler differentials, which is an A model, and by the definition, it co-represents the functor of derivations with values in a model. So in A mod from omega A to some A model M is isomorphic to derivations with values in M, which is the same as the following: as the set of maps from A to the trivial square zero extension of A by M over A. And let me say that trivial square zero extension is defined as follows. As an A model, there's just the direct sum, and multiplication is defined by the following formula. So let me show you an example. If A is a polynomial algebra modulo a bunch of equations, then Kahler differentials of A is a free A model on generators which we call the RAM differentials of the generators of the algebra. Modulo the following equations. they are denoted by d derived of f1 and so on, d derived of f sub m. And by that I mean that we just take a polynomial and compute the sum over the generators of its partial derivatives times d derivatives of the generators. Oh, so let me change the index here to j. So that's what some standard computation gives us. So in classical geometry, Kahler differentials are useful when we want to study deformation theory. And I'll let you know more about that later, closer to the end of my talk. But now I just want to say that it happens so when we want to study a deformation problem that is not smooth enough, or maybe it has some stakiness in it. Maybe objects that we want to deform have some higher automorphisms. Then Kahler differentials are not quite good enough, and it happens so that we need to derive the functor of Kahler differentials, so to say. That's what people call the cotangent complex. This is the derived functor of Kahler differentials. You might think about it that way. So let me write it as a goal. So we want to derive the functor that takes an algebra, it sends it to the model of Kahler differentials of that algebra. And we'll talk later about applications of that, but in what will follow, I want to focus more on the definition and proving existence and properties and doing basically some foundational stuff. So let's call it another section.
I'm sorry, may I ask a question?
Yeah, sure.
So how this definition relates to the very simple definition with the augmented algebras? I mean, in this polynomial example, you sort of implicitly take the augmentation of evaluation at 0, but
could you please repeat your question?
Yeah, so my question is that I guess we can define the module of Kahler differentials for a map between two rings, and for example, for this polynomial case, you do it for the map to the field, which corresponds to evaluation at 0.
Actually, I'm sorry to interrupt you. It's the other way around. We do it for a map that goes from the base field to A. Not yeah. So it's in this case, in my notation, what is in my notation, omega A is what other people might call is omega A over K.
Oh, I see. I just thought that this thing that you wrote down is naturally isomorphic to the quotient of the augmentation ideal modulo the square of this ideal, but
yeah, that's true. That's what you're referring to is what people classically call conormal sequence, I guess. Is this true? So yeah, so what you're asking, it has to do with some properties of Kahler differentials, which I don't want to recall right now, but we'll get to that when we'll talk about properties of the cotangent complex.
Yes, thank you.
So let's start with the definition. And first, let's we need a certain replacement for. We need to define what our commutative algebras will be. So I would like to work with connective differential graded algebras. Okay, there are other options, and I think most of them are more or less equivalent. But let me write it. I want to work in the infinity one category. Of connective commutative differential graded algebras, which are, you may think about this category the following way. Take just plain category of commutative connective differential graded algebras and invert quasi-isomorphisms. So if you want more details, I can say to you that there is a model structure on the right hand side. By the way, connective which I denote with the superscript not greater than 0. It means that our algebras, our differential graded algebras, have no cohomology in positive degrees. And what I was talking about is there is a model structure on the category of connective commutative differential graded algebra on the usual one category, which we start with. And vibrations are degree-wise epimorphisms. And weak equivalences are quasi-isomorphisms. And I can even tell you what are the cofibrations in this model category. And up to taking a retract, each cofibration looks like this. You take an algebra and you inductively freely add to the algebra new generators, and you prescribe values of the differential on these new variables. That's what people sometimes call quasi-free algebras, and relative quasi-free algebras are cofibrations, and all cofibrations look look like this up to return. So, and this model category, it even has a simplicial enrichment, and in terms of which you can compute the mapping space in the infinity one category. But so be that as it may, I will assume that there is a category like this, which I'm going to work in, and let's define the cotangent complex. But maybe first, I'll give you an example. Maybe let me take some interesting but simple discrete commutative algebra and computed cofibrant resolution in the category of connective differential graded algebras. So let's take the simplest singularity which is out there, and this is this Nadal singularity, and I claim that there is a differential graded algebra, a quasi-free differential graded algebra, which has three generators, x, y, and z, and there is a unique relation, differential relation, which says that differential evaluated at z is equal to x times y. And let me also say that degrees of the generators are as follows. Degree of x is equal to degree of y is equal to 0, and degree of z is equal to 1. And the underlying complex of A tilde looks like this. It has...
I'm sorry, shouldn't the degree be -1? If you just...
Thank you very much. It's -1. Yeah. Okay. According to the conventions fixed, it's -1. Thank you. And the underlying complex looks like this. It has k of x and y in degree 0, and it has z of k x y in degree -1, and the differential sends z to xy, and it has nothing in degrees which are strictly less than -1, because that squared is 0 for degree reasons. That z is not variable, so it anti-commutes with itself, so that square has to be 0. So the algebra has nothing in degrees which are strictly less than -1. Okay, so let's proceed to the definition of the cotangent complex. So let's define a functor. So the definition will be similar to the definition of the Kahler differentials. However, it will be homotopy invariant. So let us fix an algebra, a connective, commutative, differential graded algebra. And let us define a functor of derivations. This functor, it has values in connective differential graded modulus over A, and it takes values in spaces, and it sends a module M to the mapping space in our category of algebras over A. So this is the category of algebras equipped with a morphism to A, is a map to A, or a comma category, in other words. And we want to take a mapping space from A to A extended by M, where again, this notation means trivial square zero extension of A by M. And we want to define the cotangent complex as an object that co-represents this functor. So we want L sub A, which is the notation for the cotangent complex, to be the object that co-represents this functor. And now I want to spend some time proving that this object, in fact, exists. So,
sorry.
Yeah. Sure.
Could you give an example of AM?
Sure. For example, so again, okay. I can tell you what the definition is. So AM is just A plus M is an A module. However, you define sort of a the following multiplication on that direct sum.
Yeah, okay.
Let me repeat it in case maybe someone will find it useful. And that's the multiplication which makes that direct sum an algebra. And maybe example, like the most trivial example is epsilon, the algebra of dual numbers, which is by definition it is kt mod t squared, and you can write it as k, the base field, extended by one-dimensional K vector space. So in other words, K extended by K. Does that make sense?
Yes, thank you.
Okay. So let me repeat that I am going to spend some time proving that the cotangent complex, which we want to define by this universal property, exists. And the proof starts with the following lemma. L sub A exists when the algebra A is free. And the proof turns out to be pretty formal. So we start with by the hypothesis, A is a free commutative differential graded algebra. So A is a free algebra generated by some connective K vector space, connective complex of K vector spaces, the category of which I denoted by this. And the proof is formal. Let's just compute the mapping space. So what we are interested in is maps in this comma category from A to A extended by M. And recall that free, taking a complex to a free commutative algebra is a left adjoint, and its right adjoint is given by the forgetful functor, which sends an algebra to the underlying complex. So by the adjunction, we can rewrite it as the mapping space in the category of vector spaces over A from V to the underlying complex of the trivial square zero extension. But then I would like to recall that the underlying complex of the trivial square zero extension is just the direct sum. And in conjunction,
sorry.
yeah.
What
Sure.
is an adjunction you use here?
Let me write it somewhere. So there is an adjunction whose left adjoint sends a complex to a free algebra generated by that complex. And the right adjoint is the forgetful functor. It sends an algebra to the underlying complex of the algebra. And it's also formal.
Yeah, got it. Thank you.
Yeah, thank you for the question. It's also formal to check that for an algebra, A, not maybe let's use a different notation. For an algebra B, the adjunction extends to the adjunction between comma categories. Right here on the level of B. here we have 3, which basically sends, so it sends a complex equipped with a map to an algebra generated by the complex equipped with a map to the algebra. So the adjunction extends to the adjunction between comma categories, which is far more to check. And let me get back to my proof. I was using the adjunction to rewrite my mapping space as a mapping space in the category of complexes. And now, using the fact that the underlying complex of the trivial square zero extension is the direct sum, I can get rid of this A and this A. So I can rewrite the mapping space as maps in the category of complexes from V to M, which is again by adjunction is the mapping space in the category of A modules from 3 A model generated by B to M. So I conclude that the cotangent complex of A indeed exists and is given by the 3A model generated by V. So that's the end of the proof. So with no questions, let me then talk a bit about some functoriality of the cotangent complex. So far, we only, by the virtue of that lemma, we only defined the cotangent complex on the full subcategory of the category of algebras generated by 3 algebras. And I want to make a note that the cotangent complex is indeed functorial when we restrict it to this category. And I will use it later in order to finish the proof that cotangent complex exists for all algebras. So let us denote C-alg connective and 3. Maybe let's first fix an algebra B. And let us denote C-alg connective and 3, the full subcategory in the category of connective differential graded algebras spanned by 3 algebras. And the following lemma makes precise what I mean by the functoriality. Sending A to B times over A with LA. By the way, all tensor products are derived, but I might forget to make it precise in my writing, but should keep in mind that. And sending A to B tensor over A with LA defines a function. From CL connected and free to B models, maybe also connected. And the proof is again consists of checking that some universal properties agree. So let's start with the following. Let's compute maps in modules from B A over N to some model N. And this is by the adjunction is maps in the category of A modules from LA to N. And this is again by the adjunction that we used in the proof of the previous lemma is the mapping space in the category of complexes over A from V to A extended by N. And this one we can rewrite as the mapping space in complexes over B from V to B extended by N. And finally, I want to use the adjunction again in order to write this as a mapping space in the category of algebras. Over B from A to B extended by N. And so the isomorphism of these mapping spaces gives me my functoriality. And that ends the proof of the lemma. So any questions about that?
This
If not,
functoriality follows from the functoriality of Bn or something like this.
oh, yeah, so basically, what do I use here is that first, B is fixed.
From
And
derivative of pre-sheaf on Bn.
Yes. This is some manifestation of the Yoneda lemma, I guess. So this isomorphism, which I wrote at the bottom of the screen, is natural in N, and it is also natural in A. So that's kind of, and the right hand side is also natural in A. So that's what I want to use as in order to prove that the left hand side is also natural in A.
Yes.
Yeah. So this is something similar to the Yoneda lemma, I guess. Okay, so if no further questions, I would like to use this lemma in order to prove another lemma. And we are almost there. And let A some algebra, some commutative connective differential graded algebra, and let it be written as a co-limit of free connective commutative differential graded algebras. Then the cotangent complex of A exists, and it is given by this co-limit. And the proof will use concurrentiality from the previous lemma. Not just the proof, the statement actually already uses it, because a priori it's not obvious that a diagram of commutative algebras induces a diagram of cotangent complexes, and that we proved in the previous lemma, at least in case where the diagram of algebras consisted of free algebras. And the proof is the following. Let's compute the functor which is co-represented by this co-limit. So first, I will pull the co-limit out as a limit. Then I will use adjunction. Finally, I will use the.
Sorry, the right adjoint will be home, and you identify this home with them. Something.
No, not quite. Let me. let me maybe recall what it means. So if I have a map of algebras from beta C, it induces an adjunction on the categories of modules. And the left adjoint, it goes from B modules to C modules. And is basically the tensor product, the derived tensor product. And the right adjoint is the forgetful functor, or in other words, the restriction of scalars. If you have a C model, you can view it as a B model via this map. So people sometimes call it restriction. And that's the adjunction I use in order to get rid of this tensor product. Okay, does it answer your question?
Yes.
Okay. And I apologize for being a little bit sloppy and not keep like omitting the forgetful functors from my calculations. I hope it's not very annoying. So it would be, maybe it would be better to write it as res actually, but if there are no complaints, I will keep doing what I was doing. And now, by the universal property of the cotangent complex, which we know exists for AI because it was free, we can rewrite this mapping space as the mapping space in the category of algebras over A. Yeah. No, not yet. Let's write it as follows. To give more details,
these functors are between derived categories. Yes, and
yes.
So you probably you should take some replacements in variables of functors.
Well, when you compute the values of a functor on some particular object, yeah, you will need to take the cofibrant replacement if you are computing the left adjoint. But now I'm just computing the mapping spaces between some objects of infinity category, and so I can keep it implicit, so to say. So there is a way to compute the functor, which I don't care about right now.
Okay.
And in fact, even in this case, LAI will be perfect. So there will be no need to take the replacement in this case particular. So, but yeah, in general, if you want to compute it, you need to take resolutions. But
LAI is a cofibrant.
Yeah, it is. In fact, it is.
This is some sort of statement.
Yeah, at least the way we wrote our formula for it in right here in the proof of the first lemma. it's a free A model. Of course, it is covariant.
Yeah, okay, thank you.
But like computational aspects are not important for the proof. So all of the computations we are currently doing are homotopy invariant. So values of some functors which we write down are not dependent on which particular resolution we take. So first, let me recall to you that if A sub I was a free algebra generated by VI, then the cotangent complex of this algebra is the free module generated by this VI. And I can write this mapping space as map in the category of complexes of K-vector spaces from VI to M. And I can further write it as the category of complexes over the underlying complex of the algebra A from V sub I to A plus M. And then I can use the free forget junction and write it as the mapping space between the mapping space in the category of algebras over A from AI to A extended by M. So yeah, and at some point I forgot to write the limit. So let me get it back into the picture. So here we're taking limit over I as well as here. And here. And here. And now we can pull the limit back in as a call limit. And past that call limit, and we will get the mapping space in the category of algebras over A from A to A extended by M, which kind of what we aimed for. And this finishes the proof of the lemma. So let me state quickly the main point. We wanted to prove that LA exists and is given by this formula. So, and what we actually did is we took the right-hand side of this formula and computed the functor that it co-represents. And it turned out that it co-represents this functor, which is the functor that we defined the cotangent complex to represent. So that gives us the claim. Any questions about that? Okay, good. So Finally, there is a corollary which says that a cotangent complex exists for each A. And how we are going to prove it. So again, recall that there is a free forget adjunction, which we have already seen today many times. And let us denote by F the composite of free and of the left adjoint followed by the right adjoint. So it is a monad that acts on the category of complexes. And we know what it does. It sends a complex V to this. And there is an interesting fact about this monad. So just a second. Yeah. But maybe I wanted to do it differently. Yeah, I'm sorry. Probably I wanted, let's say, okay, let's denote by G the commonad. Yeah, the commonad, which is given by the composite of the right adjoint followed by the left adjoint. And this commonad acts on the category of algebras. And it sends an algebra to the free algebra generated by the underlying complex of the algebra we started with. And what's interesting is that for an algebra A, there is an augmented simplicial object. Which is given by applying the commonad to the algebra. And what's actually interesting about this simplicial object is that if we truncate it and pass to the colimit will get the algebra A. So in other words, the natural map from the geometric realization to A is an equivalence. And let me say a few words how to prove this claim. So it's a bit standard, but it's very useful and interesting at the same time. So I want to say a few words about the proof. So first, what we need to check is that the forgetful functor preserves shifted colimits. In other words, we can say that it preserves filtered colimits and geometric realizations. And it does so because the monad preserves shifted colimits. And this is a somewhat standard statement about the algebras over a monad. So let me mention that the category of commutative algebras is the category of algebras over the monad F, more or less by definition. And there is a theorem that says that whatever the class of colimits that the monad preserves, the forgetful functor from the category of algebras over the monad to the underlying category will preserve. So this is kind of a trivial statement in the classical category theory, because like algebras over a monad, just a categories of some diagram. Yes, a category of some diagrams, and the diagram is basically you have an object V, and you have a map from F applied to V, and the forgetful functor just forgets the map and sends the diagram to V. And basically, if we can compute the colimit of diagrams term-wise, which happens when F preserves some particular type of colimits, then the forgetful functor will preserve this type of colimits. So that's basically some type of diagram chase, some simple type of diagram chase in the classical category theory, but it needs a bit of a more technical proof in the higher category theory. And I want to give a precise reference to this. It's proved, a similar statement is proved in higher algebra by Jacob Lurie, and it is proposition 3.2.3.1. So you can have a precise reference if you're interested. So yeah, by the virtue of that remark, it suffices to, and also because the forgetful functor is conservative, it suffices to prove that the statement holds after we applied the forgetful functor to the whole thing. And this takes place in the category of complexes, and geometric realization in the category of complexes is just given by the total complex. So what we need to do is just write the total complex for the whole augmented simplicial objects and check that it is contractible. And the contracting homotopy, like one can write a contraction homotopy precisely with an explicit formula. And I also want to give a reference for that, and it is the paper by Bar and Beck, and it is called Homology and Standard Constructions. And you can find somewhere in the introduction the formula for the contracting homotopy. So that more or less proves the claim. And let me recall what the Kahler stated. It claimed that the cotangent complex exists for each A. And now I can use the claim. So by the virtue of the claim, I basically able to write any algebra as a co-limit of free algebras. And then we can refer to the first and the third lemma and conclude that the cotangent complex of A exists and is given by some co-limit formula. So that's the end of the proof, I guess. So any questions about that? Okay, good. So we finished with the proof of existence. And now we are ready to talk about some basic properties. So first, the first property I want to mention is functoriality. And changing A to, let's fix an algebra B and sending A to B times LA over A defines a functor. From the category of algebras over B to the category of B modules. Connective. Whatever. So the proof is similar to the proof of the second lemma, where we proved similar statement, but for free algebras. And I would like to skip that for now. And let's discuss some other properties. And the most important property is that it preserves colimits. That's an important property because it actually allows to compute it. And by that I mean that if A is written as a colimit of algebras, then LA is equivalent to the colimit of A times Li over AI. And this also more or less follows from the kind of arguments that we were dealing with. So I don't know, maybe I want to write it down, maybe not. Do you want to see the proof of it? Okay, maybe let's skip it for now. It's more or less repeats the proof of the of which lemma? Yeah, of this lemma, of the third lemma. It more or less repeats the proof of lemma 3. So let's maybe skip it for now and get to some more exciting stuff. So in particular, I would like to mention that specifically it preserves push-outs. And which means that if I have, also recall that push-outs in the category of commutative differential graded algebras are given by tensor products. So this is a push-out diagram in the category of commutative algebras, and the tensor product is of course derived, as everything in our talk. Such a push-out diagram gives rise to a push-out diagram in the category of modulus over the tensor product. And the diagram is the following. So that's the application of the previous property. That's a particular case of the previous property, how to say. And it actually allows us to compute the cotangent complex. And let me give an example. Remember that algebra, that cofibrate algebra that we saw closer to the beginning of the talk. We took a simple singularity and we computed its cofibrate resolution in the category of connective commutative differential graded algebras. And this was a quasi-free algebra on 3 generators, one of which had degree of -1, and differential on that variable was given by x times y. And let me now do the following. So I can rewrite a tilde as a push out. So I can view a tilde as if I took a free commutative algebra on 2 generators, x and y, and added another generator to it. And this actually could be stated as the following push-out diagram. where in the left bottom corner, I take free algebra generated by one element of degree -1. And the diagram, like the map sends the generator to, just a second, what it does. Yeah, I was wrong. We need in the left bottom corner, we need to take free algebra generated by one generator of degree 0, and the generator is sent to x times y. And here we write free algebra generated by the complex, which consists of two terms and has identity as a differential. And the right term sits in degree 0 and the left term sits in degree -1. And this map sends, and the left vertical map sends the generator to the generator of degree 0. And taking this push out is basically adding a third variable to the algebra that's in the right bottom corner and setting its differential to be equal to x times y. So, which is basically the definition of A tilde. And now this diagram allows us to compute the cotangent complex of A tilde. And basically it means that, let me maybe write it, that A tilde is given by the cofiber of the following map. So it is a free model on two generators. Free A tilde model on two generators. Here we have also free A tilde model on this complex. And this term corresponds to the left top term of the push-out diagram. And here we have something that corresponds to the left bottom corner of the push-out diagram. And it is just the free A tilde model on one generator. And the map from A tilde from this term to this term is just given by the inclusion in the, just given by the isomorphism, by the identity in the 0th degree. And map from here to the left part is basically given by taking this element and evaluating the universal derivation, which is a derived differential on this element. So let me write it. Yes. So one here, it goes to J-germ of xy here, which is derim of x times y plus x derim of y, which is not hard to check, I guess. So that gives me the formula for the cotangent complex of A of A tilde. But maybe first what I wanted to do, what I actually wanted to do is to compute the cotangent complex of A. And this is because A is quasi-isomorphic to A tilde. It is given by this formula. And I want to write an explicit formula for this complex, which is according to the calculation is a quasi-free A module whose generators are derim of x, derim of y, and derim of z.
I'm sorry,
yeah.
maybe that's a stupid question, but shouldn't this map be a map of algebras over
Which
K?
one?
Well, at least the blue one, I think.
No, it's a map of modules.
Oh, it's just a map of modules.
Yeah,
okay.
Sure. Because we're computing the model, so it's a map of modules. Yeah. It's not
Okay.
So sorry, and the isomorphism, the top isomorphism between LA and the cofiber is derived from the push-out diagram. Am I right?
Yeah, sure. You're absolutely right. This
is a cofiber between cofibers. Yeah.
It's a cofiber of map. So in a stable category, which the category of models is, computing pushouts is the same as taking a direct sum of these two terms and computing the cofiber of the resulting map from the left bottom term to the direct sum.
Probably it is equivalent to take a cofiber between cofibers of horizontal maps.
Maybe, I'm not sure.
Yeah. Thank you.
Okay, thank you for the question. And what I was getting at is, I was trying to write a formula for the cotangent complex of A, which is the cotangent complex for A tilde induced to A. And the formula is that it is a quasi-free A module generated by three variables, derim x, derim y, and derim z. And there was a unique relation of the unique differential relation, which says that differential of derim z is given by derim x times y, which is x times derim y plus y times derim x. So that's a nice formula, which for do I have 15 minutes? Am I right?
Well, probably yes, but you can go as long as you want, so there is no restriction.
It's probably not a very good thing to kind of be substantially over time, so I will finish in 15 minutes. So
yeah,
what I want to do is I want to finally get to some interesting and funny applications of the theory, and the application is the application is to the deformation theory. And let me briefly mention the the classical story. So recall that if X is a smooth scheme over K, I can consider its first order infinitesimal deformations. Which are families, flat families, maybe not better to write X prime over the dual numbers, such that X is isomorphic to the fiber at the point. And there was a computation, a classical computation in the deformation theory, that the set of such first order deformations is isomorphic by the first cohomology of the tangent space, of the tangent sheaf, which is dual to the sheaf of Kahler differentials. Just look home from the sheaf of Kahler differentials to the structure sheaf. And in particular, if X is affine, then there are no non-trivial infinitesimal. There are no non-trivial deformations, basically.
So sorry,
and yeah,
omega x1 is an associated sheaf with the functor omega x1, yes. Or
yeah. So it's a sheaf of Kahler differentials. On an affine open, it sends an affine open to the module of Kahler differential of the algebra of functions on the affine open. So basically, if X is spec A, then omega 1x is omega 1a, the module of Kahler differentials, which we quickly studied at the beginning of the talk. So, and what I wanted to say is that if X is affine, smooth and affine, there are no cohomology, there are no coherent cohomology, and all of the deformations must be trivial. And this statement, it fails when X is not smooth. And that's where the cotangent complex comes into the game. And let me briefly define the corresponding deformation problem in a homotopy invariant way. So now we will be deforming an algebra, not a scheme, because we didn't define schemes. We only talked about algebras throughout the whole talk. So we will try to deform an algebra. So let's fix a commutative algebra over okay, commutative differential graded connective algebra. And the functor of deformations of A, it is a functor from the category of small, augmented, and connective differential graded algebras to the category of spaces. And small means that small basically means Artinian. It means that the total cohomology of an algebra is finite dimensional over K, over the baseband field K. So basically, we are talking about Artinian algebras, but about Artinian differential graded algebras, generators that are allowed to live in non-positive degrees cosmologically. And these algebras are also required to be augmented as well. And the functor sends such an algebra to a space of deformations of A over C. So it is a space of such maps from C to A prime, together with an isomorphism. Of the central fiber with A. And it's actually needed to be checked that it is a priori, this defines a category of such pairs of the category of such maps from C to A prime together with some isomorphism. A priori, it's a category, but in reality, it is a space. It needs to be checked. That's some statement about the infinitesimal geometry of a point, so to say. Okay, so, and there is a point spec K of depth A, which corresponds to the unique trivial deformation over K. And it can be checked, it's pretty formal, that if we look at that point, our deformation functor, we will get functor of infinitesimal automorphisms of A, by which I mean that out in A of C fits into the pullback diagram of spaces. This is map over C from C. This one, this diagram. And it is in fact it is a fact that out inf A is a formal group over a point, whatever that means. There is a good notion of a formal group, which is defined in the second book by Gaitsgory and Rozenblyum, where the foundations for this kind of stuff were laid out. And what I wanted to do now is observe the following. So I can rewrite formula for the values of this group on an algebra C as follows. It will be, first, I can get rid of by the fact that the tensor product in the category of algebras is a push out, I can get rid of the tensor product and at the same time get rid of that over C mark. So I can rewrite out inf C as something that fits into, maybe let me write it right here. So I can rewrite this as map from A to C times A. And then I can observe that it gives me a formula for the values of the group on C, which computes it as the mapping space in the category of algebras over A from A to C times A. In particular, if C is the algebra of dual numbers, then out in A evaluated on the algebra of dual numbers gives me the mapping space in the category of algebras over A from A to A extended by to A epsilon, which is the trivial square zero extension of A by A. And this is the same as maps from the cotangent complex to A, which is a generalization of this classical statement for an affine X. Because for the following reason, because out in A was a loop group of the functor of deformations. We kind of observe from the computation that def A evaluated on the algebra of dual numbers gives us, what does it give us? Yeah, it gives us map A mod from A to A shifted by 1. Because looping in a stable category is a shift by -1. So D-looping is a shift by 1. Okay, so in particular, by 0 of this space is, how to say it? Yeah, this is, if I define the tangent complex as a dual to the cotangent complex, so I need to take local home over A from LA to A. Then by 0 of the deformation functor evaluated on the algebra of dual numbers gives me the first cohomology of the tangent complex. And let's finally 1 minute getting back to the example of a simple singularity that we studied. So recall that A was kx y xy, and A was free model on free generators, model of the relation, and TA will be free A model on free generators this two has degree 0, and this one has degree 1. And the relation, there are two relations. The first is d of dx is, I guess, it should be y dz. And the second one is d of dy is x dz. And in particular, we see that h1 of dA is isomorphic to kxy modulo x and y, which is isomorphic to k. In particular, we see that there is indeed an integral deformation of this algebra, which is in fact true, and it could be computed by this formula. So, thank you very much for listening. That's it, I guess.
Okay, thank you so much for this wonderful talk, and let's thank the speaker. Okay, so I guess if there are some questions, then probably it's a good idea to ask them right now.
Yes, my comment about pullback was wrong. All right.
Oh, that one about the. Okay, let's see. About this diagram and this cofiber.
Yeah, it was a mistake. Sorry, my comment was wrong.
Never mind that. It's okay.
Okay, if there are no more questions, let's thank the speaker again.
Thanks for coming.
Yeah, okay.